All right, so this is a little demonstration of our next unit for astronomy. This is an extension of the force stuff we just finished up. We're going to be applying it to some bigger celestial bodies and looking at the force of planets and stars and consider our place in the universe. I'm going to give you a few demos here of a few programs. These are all free. You can download these on your devices and play around with them. This first one is called Stellarium, and we're here in this field. And as we move it around, it's a 360 view. But what's nice about Stellarium, we're in Goldsboro. I don't know if you can see that on the screen. Yeah, you can. But we can fast forward time. And obviously, watching stars at the daytime isn't very interesting. But here's tonight's view. So we got Mars out tonight, a couple of stars, and just gives you a nice view of the stars from our perspective. This particular program, you can, let's pause time so we're not moving. Let's zoom into Mars. This particular program, you can you just lock on it. There it goes. And we can zoom in and see what's up to Mars and get a lot of information here on the side of its astronomical data, its brightness, its magnitude, and spectral class and all that stuff is great. See some of the moons, how they orbit. But if you zoom out, you see all kinds of things and watch the patterns every day, kind of see where the stars are at. That's how they did ancient astronomy and trying to figure out what's causing this motion. They are orbiting our planet from our perspective. Obviously, we know a little bit more is going on than from the early astronomers. This particular program, you can turn on some constellation lines. Maybe you want to see some of the star shapes, or more impressively, the constellation art, so you can see kind of what you're supposed to be seeing, dragons and bears and all that stuff. So here we have Ursa Minor. It's a pretty important star. This one right here, that is Polaris, otherwise known as the North Star, and it's called that because as you rotate, all of these stars go around that particular point. It doesn't move, it's fixed, it's lined up with the axis of our rotation. Interesting to note, it was not always the North Star, and it will not always be the North Star. A couple thousand years ago, I can never find it. It's got to be the one in its claw, right? One of these stars with the dragon is Thuban. Where are you at, Thuban? I could just type it in. No, I'm determined to find it. Oh no, we're rotating. Is it Thuban 3? I can't. There's a star in the way. I can't click on it. There it is. Thuban. There it is. So Thuban was the North Star about 10,000 years ago. It's about the time of the Egyptians and that culture. The pyramids and the obelisk in Egypt all point at this star because they do the same thing that Polaris does for us now. It's very important for navigation at the time. So they built monuments to that particular celestial body. So as we have the day go, you can see all the rotation here, and I'm actually going to turn the atmosphere off so you can see even better. They shine a little bit better. You can see the Milky Way and that kind of stuff over here in the horizon. This also means this is probably daytime now. The sun is going to be coming up soon. There she is. But it's not going to change the brightness of the sky because we turn the sky off. So this gives you a nice perspective of the planets from our house, our perspective, what we're looking at. It doesn't really give you a good view of what's geometrically and geographically going on if you think about it in three-dimensional space. So we're going to flip to a different program here and get a different kind of view that we look at here in the astronomy unit, as we're going to be tracking the forces and the motion that's keeping all this stuff rotating and moving. So once again, this one's called Stellarium. But we're going to pause here, and we're going to switch over to, hopefully, if all this works, we'll switch to Celestia. Are we in? Yeah, all right. So this is Celestia, kind of like Google Earth. We can zoom in and see Earth doing its thing. And what's cool about this one is, again, this is a 3D model. I can move it around and manipulate it. But we can, as you saw, just zoom in, and I can also zoom out. There we got the moon. We'll give it a little time. What's the command? L. I always get it mixed up. So we'll make time move a little bit. So the moon's going to start to rotate. That's as far as any human's ever been. You'll note that green line is not a perfect circle because it's an average of distance for the rendering on this program. But we can keep zooming out here, and we can get to the other planets. Here we have the sun. Again, a little different perspective. This is more kind of how you're used to seeing it in your textbook, bird's eye view from the top. And you can see all the planets there moving. There's your first dwarf planet series. We'll get to the dwarfs in a little bit. And what's interesting about these planets, especially the major planets, is they're all on the same, what we call plane. So if you rotate this to 3 dimensionals, this line right here is all of the major planets. Then you have all your dwarf planets doing kind of whatever they want to do because they follow their own dwarf planet rules, which is why they're not planets. They're got some different gravity things going on. And that's just, it's an interesting thing about the birth of the galaxies and the universes, and more specifically our solar system, is that gravity and how gravity is binding these things. You'll notice Ceres, the first dwarf planet, is also off axis by quite a bit. You could measure that angle if you had a little protractor there, figure out some deeper meaning of the universe. But interestingly enough, the planets themselves have a similar situation. So go to a big planet like Jupiter. And Jupiter has a bunch of moons, has 4 major moons. Whoa, we're moving fast. Let's slow you down just a wee bit. Okay. It's got some major moons. Those are the ones that Galileo was working on. He was looking up at the Jupiter and watching Ganymede, Europa, and Callisto, and Io. Where's Io? There's Io. And Io move. These are the major moons. You notice they're also on a plane, a disk, and we call it the accretion disk. But if I turn on the minor moons, and Jupiter has a lot of moons, about 68, I believe is the count right now. They are a bird's nest of wonky geometries and some weird things going on there as you get further from the source of gravity, which is what this whole unit is about, is not just gravity itself here on Earth, but we're more interested in Newton's, what we call the universal law of gravity, and we'll be getting to that calculation tomorrow. But in this bird's nest, at the center, just like our planets, they follow that pattern. And Saturn is the same way. Saturn has the most moons. It's about 74, I think is the count. Most of the ones in the major rings are the major moons. They're in that accretion disk. Again, even some of them are inside of the famous ring. But as you get outside of that, you get that sort of loss of control for your orbiting planet, or satellite in this case. So it's interesting. And out there in the back there, we see our next planet that I like to talk about. Dwarf planet. No longer a planet. 2006, it was demoted by the Astronomical Society, the IAU. There are 4 major moons of Pluto. The 4th one's actually not tracked on this particular program. I wonder if I can get some data. But Pluto was downgraded mainly because of its moon, Chiron, is large in the sense of this is a dime and this is a quarter, and you can even see it's pulling on Jupiter in a sense of like a carnival ride. They're tidally locked, which is the main thing that makes it not a planet. To be a planet, you have to only be under the influence of the sun as your main motion, and this one is too small. Pluto is so small that it doesn't actually get to do that because of the gravity of its moon. Now we're tidally locked as well, but we're so much more massive than our moon that we do not get pulled into a circle like that. But we are locked in the sense of we're always facing the same side of our moon as well. So what's particularly interesting about this particular program, let's go back to the sun and we'll center up on her, is, I'm going to get bird's eye here. We have all of our planets, all of our dwarf planets. We'll learn these dwarf planets this week. Maki, my favorite in here, Eris, furthest place from the sun. Pretty awesome. Is if you keep zooming out, eventually these points, you see the left-hand corner, our distance is still growing up. these points eventually collide and coalesce into a larger mass, a larger system that you're probably familiar with in terms of the shape, but this is the Milky Way, our little galaxy. Now we do have another little galaxy here coming in. Particularly, this is a spiral galaxy. We'll do a lot more on galaxies if you take astronomy here. But as we view the universe at this point, we have all these galaxies. This is where we're seeing other light from other sources that are not our own. Here's LMC. We can go center on it. Can I go to it? I don't know this. Oh, yeah, I can go to it. Okay. LMC here is a collection of stars that we've been tracking. Not stars so much, but illumination. We assume there's stars in there if it follows our pattern. It is a spherical galaxy instead of a spiral or a flat one. But unfortunately, that is the limits of our technology. We don't know the position of any of these stars, the mass, spectral class. We can't really see much further than just the fact that there's some blob of what we assume to be a cluster of billions of stars, which is the prime definition of a galaxy. But as we zoom out, that's true for any of these galaxies. There's only so much we can see, so there's only so much we can know. And particularly, if you just keep zooming out, you'll still see more and more fly by, but eventually it just turns black because we no longer have any more light. So then you can get some interesting philosophical questions of, this is the universe in any direction. I'm spinning the camera all over the place, but you can't see exactly where we're looking or pointing, but there is still space out there doing gravitational things, but we've lost our main source of science and observation, which is light. You get into the arguments of the observable universe versus the unobservable, and there's many conversations to have about that. We can have those later this week. But for now, we're gonna go back home. We can find it. Luckily, I have some keybinds here that takes us to the soul, which is the sun. Somewhere in there. There she is. Okay, we're home. We're good. All right, cool. So, what we're going to be doing this week, we're going to be looking at primarily our solar system. There are, some motions happening here, right? This is still physics. Let me speed up time a little bit. And the motion that we're seeing here is one, you see some centripetal motion right there right off the bat. So anytime there's anything in a circle, there is a centripetal force. But for us here, there's also a gravitational force, right? These things are massive. Obviously, our Earth, our planet, we know our gravity, what it's doing. We've done quite a few experiments with that. But the other planets have their own gravity, and they're all bound to the sun, and we're all bound to the center of our galaxy. So there's something more fundamental going on here in the sense of the motion we're observing. So we're going to observe these motions. We're going to start with Newton. He has another law, the universal law of gravity. We'll get into the math here in a little bit about what's keeping this force, what is this force that we're measuring here. And then we're going to get into another astronomer. His name is Johann Kepler. He was basically looking at the geometries of these rotations and that they're not circles and what that actually implies as far as the motion that you can observe for finding velocities and accelerations and other kinematic functions as well. So we're going to get into some of those. We're going to do two of his laws. He's actually got a third, but I'll just explain that one to you. We're not going to do the lab on that one because that math is super fun. But we'll do the universal law, Kepler's first and Kepler's third. That'll be the three astronomy labs.